morning, good afternoon, good evening for everyone where you are. I will start share my screen. Please let me know if you can see my screen right now.
Yes, we see it.
Okay, perfect. So, my name is Alfonso Rodriguez. I am the Global Strategy Coordinator and the Country Director in Colombia for Pure Earth. First of all, I want to thank all the members of the Secretariat Minamata Convention for organizing these side events. This week has been very great and wonderful because we be able to learn, know, and share more experience around the world in different spaces in order to know more of the prevention. I use the mercury around the more around the work in some issues. On this first part, we will present with my colleague John Kitt the development of the Mercury Contamination Index to estimate the risk public health from ASGM activities. This work is under the Planet Goal Initiative and also is financed by the funding coming from the UNDP Colombian office. Um, the short agenda for this first 30 minutes is a very brief Colombia context about the situation, about the mercury and the sites, some criteria for the index, then how to use the formula for the index, and finally, uh, present some result and interpretation of data from this index as well. So, since 2016, and with funding to other organizations, we are able to collect a lot of information around the identification of contamination sites in Colombia. This is a toxic site investigation program developed by Pure Earth from 2009, more or less. And from that period, we have been identified at least 72 sites at the moment. 37 sites are coming from other projects from 2016 to 2019, and 35 sites are coming from Planet Goal initiative between 2020 and 2021. And the moment we are running another project funded by the UNDP and also the Ministry of Mining here in Colombia, and we get the potential of 140 potential site contaminated to identified. We are in the process. We expect to finalize this collected data at least in 2 months. So the main reason for this site that are generated are coming from many reasons, but the principal is the pure management of tailings for coming from the artisanal gold mining. As you know, in Colombia, the use of mercury is forbidden for 2018. And, and for that period, before that date, uh, now that site are considered as environmental liability already. After that date is considered illegal mining when they use mercury. So this is a big problem here in Colombia. We keep with illegal mining, and they generate new contaminated sites. So that is a challenge for all the local institutions and for society institutions as well, because it's something that we need to keep working on that. Um, some the principal reason is because these tailings are part of the new business, underground business, because there is a lot of gold associated inside. So they reprocess the tailing to cyanidation process as well, and transportation. The tailings is not a final disposal in a proper way. So all that issue create new sites and generate more risks for the people that is exposed to these sites and tailings with huge amount of mercury inside. Um, so the main objective to create this index is to have a rapid assessment what is happening with the risks of the people that is living or work near to these sites. So the idea is to get data, to get a rapid analysis, and create a way how maybe the local government, the local institution can make decision in one site and comparison to other site. So we need to confirm the presence or absence of mercury in one site, in soil, water, or air. So we take samples. Could be with portable equipment or we send the samples to the lab. Then estimate the number of people that is on risks. That is very important. We can collect all the information with children, teenagers, adult people, old people that live in near and with the age, and also pregnant woman that is on the site because it's very important for the index. And then with all that information, we do a formula that we'll show you later on, and we create a number, a score. And that number, we can compare in different sites which site need more intervention, urgent intervention, or more careful for the people to the other. That's the idea. The original index coming from one work what we did in 2014 when John worked as well. It was called the Blacksmith Index. This index usually was developed for all the contaminants and can use and we keep using that in other aspects. But in this case, we modify this index specifically for mercury and to create the risks. So I want to give you the floor to John Kidd. He's one of the senior technical advisors of Pure Earth, and he will explain a little bit more about the criteria and how to use the formula and what is the reason of this index. So, John, the floor is yours.
Good morning, good afternoon to everyone. You're on slide 6, right, Alfonso? So I would like to describe what the Blacksmith Mercury Contamination Index is and how it's intended to be used, what's considered in this index. As Alfonso said, this index is focused on public health, and it presents a comparative risk evaluation between sites in terms of what public health risk is presented. We are aware that you could also rank sites about economic significance or how illegal they are, but this is focused on public health. We are only looking at mercury contamination. We're well aware that there are other risks related to ASGM sites. There's ergonomic risks, heat stress, all sorts of occupational health risks. There can be other pollutants, but this index is focused on mercury. We do look at, in the index, contamination of soil, water, tailings, air pollution, both indoors and outdoors. Although in practice, the air and soil and tailing contamination dominates in the index because that's the primary means of exposure that we're finding. It provides a single score for the site for all these media. Can always be a little controversial about how you compare risks from, say, ingestion and inhalation, or risk from air exposure to dermal exposure, but we do attempt to combine them into one common index score. So the next slide. When we look at a site, we have to be very careful what the site definition is. You can define sites in many different ways, and I'm going to get into that in a little more on the next slide. What we do consider when we're looking at a site, possible areas where there is mercury use and contamination, the mining activity, concentration, extraction, the burning of a mercury amalgamate, tailing disposals, and residential areas or population areas, schools or whatever that are in immediate area where mercury is used. In order to evaluate health risk, you have to say what is bad and what is good. And in the index, we use what we call reference values. taken from the literature as to what are threshold values where mercury can start presenting health impacts. We recognize that there is no zero level. I mean, there is no minimum level where mercury does not impact people, but you have to have something that you compare the level of contamination to. So for air, we use 1 microgram per cubic meter. For soil and tailings, 10 milligrams per cubic meter. And for water contamination, 2 micrograms per liter. So next slide. So the definition of a site is very important. You could say a site is huge. It's everything within 5 kilometers of where mercury is used, or you could narrow it down to a single specific activity. This is exactly where they're doing the burning of the amalgamate. For our purposes, we're using the site as a contiguous area where contamination is found. It's generally a small area. It's close to the mercury use and disposal areas. You go to a ASGM site and you'll look for where mercury was used and contamination may be. Where did they burn? Where did they dispose of the tailings? Where did they store the amalgam? You'll also look at the adjacent areas. Is there fields that are contaminated? Is there chicken coops or duck pens? Are there houses that they stored amalgamate in or tailings in? Are there schools nearby? So you're looking at all and measuring all of these areas. You're typically using a Jerome for levels of contamination in the air and an XRF for contamination in the soil. Water requires a laboratory analysis. So next slide. So this is the contamination index formula. First, within the parentheses, you'll see various letters in this. To measure the level of contamination, you compare, basically divide the level of contamination you found in whatever media. Take the level of contamination found in the air as measured by a Jerome and divided by the reference value, 1 microgram per cubic meter, and take the log of that, and that's your level of contamination for air. We take different values for outdoor air, indoor air, soil, tailings, and water. We also measure the population level. That's A2 and A3. We divide the population into 2 different categories, adults and young children and pregnant women. We give a higher weight to the child and pregnant women population. Where we find measurements in the rapid assessment analysis that are below the reference value, we use 0. So in practice, you'll say, well, there was no, for example, no residential air areas found, so there was no general exposure for air. Okay, then that gets a 0. Or there was no tailings found, so that gets a 0. So next slide, some specific notes on the mercury contamination index. And I'm going to start from the bottom of this slide and work up. We give a greater weight to young children and pregnant women. So for adults, they just get the log value of the number of people. For children, we get 3 times the log value. And that's because of the smaller body weight and greater activity that you have in children, and the fact that in children and pregnant women, the mercury exposure can have longer lasting impacts and impairing neurological development. We use a log scale when developing this formula. We've tried lots of different combinations, but but we recognize that concentrations and populations tend to increase exponentially rather than arithmetically. You either have a small village, it's got 10, 20, 30 people, or you get 1,000 people or 10,000 people. Similarly, contamination goes from very low to very high very rapidly. A logarithmic scale allows for you to keep the index that is calculated to a rational number rather than getting astronomical numbers very quickly. The overall risk factor is additive for the various different contaminants and populations. Because it's a log scale, you certainly can't multiply them together because effectively using a log is adding logs is effectively multiplying anyway. And the health risks that we actually find in the field are primarily related to inhalation. But we do consider secondary ingestion routes. So the next slide. We give greater weight in the index, twice the log value of the air pollution found for indoor contamination, because mercury vapors first are more likely to linger inside spaces. They attenuate very rapidly in the outdoor air. And in indoor spaces, you can have condensation of mercury vapors on the walls and floors. And in the heat of the day, you can have evaporation and more mercury exposure. So indoor exposures are greater and longer typically than outdoor exposures. And also people and children in particular are more likely to spend more time. And people in the immediate area, workers and people living right in the area, that's in the site definition. We are not looking at areas that are far away from the site, and far away means 100, 200 meters. Since mercury concentrations tend to attenuate very rapidly with distance. And as I said at the beginning, we're only looking at contamination and not legality or economic significance of a site. So that's a little use of this background on this index. Again, it is intended for use for ASGM sites that are investigated using a rapid assessment method. A day, several days at a site. If you have done a more detailed assessment, then you have the basis to do a more detailed risk assessment and evaluation of health impacts. But a rapid assessment is often needed so that you can determine priorities of where you want to pay the attention. And that's what this index is for. You do a rapid assessment, you calculate the overall risk index score, and you say, here's the site that's more likely to have more health impacts than other sites. Also should add that this index and the rapid assessment methodology is intended for fairly small sites. It is not intended for very large mining sites, where you have 100,000 or 50,000 people covering over a very large area. The equivalent of large Superfund sites in the United States. A rapid assessment methodology is really not appropriate when you have very large sites. So this is for smaller ASGM sites in particular. So with that, I will hand this back to you, Alfonso.
Okay, John, thank you so much. So the last part of this presentation, we want to share some specific data that we collect from some sites of Colombia. As you can see on the screen, this is the level of concentration of mercury in some sites in the Nariño part, southwest part of Colombia, and on the north part in Antioquia as well. We get some concentration, very important concentration on mercury. As John said, it's not only the concentration of mercury on soil or water or air that we account in this. We need to do the correlation data with the number of people that is exposure as well, and also with the value reference. There is a specific for Colombia. We have a problem. We don't have a specific value reference for soil or contaminants specific for mercury. So we need to take a value reference for other countries, EPA in the US, for example, and try to compare that data with ours. So the idea is to get our own reference value in the future. So you can see what is the concentration of mercury. But when you put all this information with the variables or the criteria that John just explained, the numbers can change. For example, this is a huge uh, numbers that we get from different type of calculation of the index with the criteria and the way that John explained. And we can identify that the index for one side could be different to the concentration. So this is a rapid assessment and rapid make decision issue for the government and the local government to take actions in one side. For example, you can see here on the top in Suarez, this is a municipality of Cauca. There is a place called Maraleves that is the highest number of the index. Maybe because the number of people, child or women that live in that area is very representative, and the concentration of mercury with the area that they work could be very important to an intervention. Could be a social intervention, health intervention, or environmental intervention. It doesn't matter what it is, but it's some idea. Or maybe that side need, as also Jane said, we need a detailed assessment what is happening in that area. So this is a very rapid assessment how to get that information, and we can compare many sites on the issue. This is our presentation. There is some questions that are already. There is just to finalize with some summary conclusion. The Mercury Contamination Index offer a quick estimate of the risks, and a specific population can be established. However, it doesn't replace a detailed risk assessment, to be honest. So it's only to have a quick tool. Um, for the government, I repeat, these tools can help to the agencies to prioritize urgent interventions, and update the mercury index is very achieved with incorporating specific data for food, fish, and other criteria that we want. So it could be very flexible, and that we need to get more studies and more collective data in some issue in some point. And over the time, that's also that we can use the index, because we can get a, a number now today, and after the one intervention we can again calculate the index, and we can compare through the time how is the advance of this intervention in comparison to the other side. So maybe that side that you see with 7 in some point could be 3 in, I don't know, a couple of months, a couple of years, and the future. Maybe we don't comment, but the range of the index is between 0 and 10, maybe 12, 13, no more than. So it's only 10, 13 numbers that we need to use to compare the sites. That's our presentation. There is some couple of questions on the chat. I will try to answer. One is that there is any publication of this index in the website? Yes, we will publish this all the document with all the description that we did in a short time. Maybe we keep working hand in hand with the UNDP office here in Colombia to collect more data. As I said at the beginning, we are collecting data for 140 sites at the moment, so we expect finalize this study in 2 months. After these 2 months, and I just do some adjustment of the index, we will publish on our website how it works and all the description that anyone can use. So I don't know if someone have any other question.
Yeah, I'll add that it is the intent of Pure Earth to make this tool publicly available. We have done that with the Blacksmith Index for other contaminants. And as Alfonso said, once we do some finishing the data manipulation and evaluation in Colombia, intends to have a paper and make this sort of information and the spreadsheets that calculate the index publicly available, along with the methodology for the rapid environmental assessment.
Okay, I think so. There is no more question in the chat. Okay. There is another one here. John, maybe it's for you. How is the human environment interaction taken into account in the index?
The in risk versus environmental risk, is that the question?
Yes.
This index is focused on public health risk, so it does not consider ecological risk. So the risk on to fish and wildlife and whatever is not considered. It does look at possible ingestion routes. So if the fish becomes contaminated and people eat that fish, we are looking at food sources that are contaminated as a public health risk. But this is definitely focused on public health and not ecological impact.
Yeah, there is another issue on the question, sorry, that is can be used in urban centers, maybe to modify it to get the urban centers or cities. Use this index. John?
You repeat that, Alfonso? I didn't quite.
If this index can be used in urban centers.
Oh, urban areas, yes.
Urban areas.
Yes, this index can be used in urban areas. You tend to find that if you have any significant mercury contamination in an urban area, the index values go up very quickly. That's because the population numbers are high, and you can have a lot of people that are close to the site. The real trick in urban areas is carefully defining the site. You really need to go out with your equipment, your Jerome and your XRF, and measure carefully the extent of area that is contaminated, so that you're not adding in thousands of people who are not exposed. You also need to have careful consideration of who goes to the site area and for how long. You generally would not consider people that are just walking past the site as part of the population. You want to have people that are living there or going to school there or working at the site. But it is very important to measure urban areas, sites in urban areas, and within the rapid assessment methodology, the trick is carefully defining the site and the exposed population. But once you've done that, yes, this index can be used in more urban areas.
Okay, thank you so much, John.
Alfonso,
Yes. We're done.
You have only 20 minutes, I think 30 seconds. So I think there's another question on what are the extent of mercury pollution in wetlands, but you can respond in the chat. So
Okay,
yeah, at 1 o'clock sharp, I would like to hand over to CSF. So if you can conclude this session with some words, please.
No, thank you so much. That all the floor is for Pedro to continue, and thank you so much for this space and share this tool with everyone. Thank you so much, Sako. That's it.
Thank you. Then Pedro, yours.
Good morning, good afternoon. First of all, thank you very much for the invitation and the opportunity to present. My name is Pedro Gasparinetti. I'm an environmental economist and country director for CSF at the Brazilian office. Today I will present the mining impacts calculator tool. Please let me know if you all can see the shared screen. This was a tool developed in partnership with the Public Prosecutor's Office in Brazil to assess and to value impacts of illegal small-scale gold mining in Brazil. Just a quick introduction, Conservation Strategy Fund is an NGO based in Brazil with office in different countries. Here in Brazil, we work with environmental valuation, impact assessment of infrastructure projects, and design of economic incentives for conservation. Today I will present the online calculator, which is based in this study that we have recently published. We are publishing a series of studies actually based on the whole calculator idea, and one of its components is related to the economic impacts on human health resulting from the use of mercury in illegal gold mining in the Brazilian Amazon. So a little bit of background. In Brazil, illegal gold mining is expanding quickly in the last few years, and illegal here in this case is often is related to mining that has no license to operate, and that is often occurring in indigenous land. So it's an illegal activity that goes to illegal sites where it wouldn't be allowed such type of activity. And some public agencies and institutions in Brazil, such as the Public Prosecutor's Office and the Federal Police, are working to prevent this type of activity. And one of their strategies is to apply some fines to the people responsible for these invasions in indigenous land and contamination. And a challenge that the Public Prosecutor's Office and the Federal Police had was the lack of a standardized methodology to assess these impacts in terms of deforestation and also mercury contamination. As we have a lot of different spots of illegal gold mining in Brazil, it would be very time consuming and to apply evaluation to all these different points. And due to the lack of methodology, the public prosecutors had a lot of difficulties to sustain the claims in courts, these fine amounts in courts. So the idea was to create a standardized formula with generalized parameters from literature reviews, basically, and interviews with miners to validate some parameters. So what we did was sort of a value transfer formula with a range of values of parameters that linked different context values to different values, impact values, economic values. The potential uses for this calculator first is to set penalties and fines related to the environmental and health damage, the average damage that is expected to occur in a given size or amount of gold that is extracted. It can also be useful for agencies who want to have more or to ask for more resources from governments to prevent these. So the calculator can show the cost of inaction and then show that investments to prevent these activities are worthwhile. And lastly, it can support also changes in regulations, such as reducing the amount of gold, of mercury that is used. So in Brazil, it's still legal to use mercury if you have a license for it. And then we can demonstrate that reducing mercury use can lead to smaller social damage. So I'll quickly present an overview of the calculator. You can find it in the link that I put in the chat here. So the tool is also meant to be not only an analytical tool, but also a pedagogical tool to explain to a layperson how the damage was calculated, the values were calculated. The calculation is done for 3 types of impacts. So deforestation, sedimentation of rivers, and mercury contamination. We use some context values, basically depending on the municipality where the illegal gold mine occurs, which will influence variables such as the density and size of affected population, average fish consumption, which will lead to different health outcomes, transportation costs for restoration of impacted areas, and we also have other variables that will influence values such as the type of mining and the unit of measurement. And here we can consider, as I mentioned before, we are using a range of values, and we can use like average values. In the case of public prosecutors, sometimes they seize gold during transportation, so they don't know exactly where the gold came from. So this was a big problem, and because of that, we also have these. We try to build this formula in a very general and with average values. So if we don't know exactly where the gold came from, we can consider general average impacts and parameters. And if we do know, we can choose the state and municipality. There's an option also like to define the type of mining, which will result in different types of impacts. So alluvial, boat mining, and peat mining. Here, let's use alluvial, which is the most common type of mining in the Brazilian Amazon. And the input information here, we can include the impacted area size. So what is the area and pit depth of these alluvial gold mine, for example, or in the case you don't know exactly where the gold came from, we can choose the amount of gold that was seized, for example, during transportation. So let's see the average impacts of 1 kilogram of gold in using this standard pit depth. So here the calculator uses these average values to calculate impacts from deforestation, erosion, and silting, and mercury contamination. Here we try to explain graphically a little bit of the ecosystem services that we considered. So we considered the opportunity costs or the value of the benefits lost due to deforestation in terms of carbon stocks, opportunity costs of low timber forest products, etc. And we consider, as this is an illegal activity, the restoration costs. And while the restoration is not completed during a 30 years period, we consider partial opportunity costs. And here the calculator provides economic and monetary values for subtypes of impacts in an additive way, additive formula. Here we have the same rationality here for siltation. So here we provide very general expected values, right, for the extraction of 1 kilogram of gold, how many hectares would be deforested, how many cubic meters would be eroded. And here the same rationality here on the opportunity costs of ecosystem services and restoration costs of the components of soil and erosion. And lastly, we have mercury contamination, again, with very general and average values. 1 kilogram of gold in Brazil uses on average 2.6 kilograms of mercury, which 30% on average, again, goes to the water, to the rivers. And of those, 3%, based on literature and studies, are methylated and become the toxic form of methylmercury. So we develop a very simple model. It's the first model that tries to link this responsibility I mean, the additional mercury from the artisanal small-scale gold mine and not natural mercury to what people consume on average. So we have in Brazil this average contamination from population, which varies from urban population and rural population or indigenous population. And basically, we estimate that from the mercury used in these mines, the average, on average, over the lifespan of methylmercury, 0.4% would be at some point during all the lifespan of methylmercury that can go over 100 years. 0.5 would be consumed by humans that eat fish. So again, this is a very average estimation, but that allowed us to estimate the change in the risk, relative risk of developing some health outcomes, such as neuropsychological problems, loss of IQ in children, and increasing the risk of developing cardiac diseases and hypertension. And here we have this subtype of impacts. We present all the references here, the key references and hypotheses also in the online tool. And lastly, we have the summary of results, where you can easily change here from type of mine, of pit depths, etc. And we also consider different hypotheses. As I mentioned, we have a range of parameters. We can consider the average parameters or the maximum values following a precautionary principle, for instance. So this is a summary of the calculator. I will continue with a little bit of results and a case study. So the overall result is that the current illegal artisanal small-scale gold mining in Brazil generates, on average, a social cost in terms of environmental losses and health impacts that are at least two times greater than the private benefits of selling the gold. So I will present a little bit of the methodology here very quickly. So first, we needed to estimate the productivity to establish the equivalence between mining area and gold production. You can imagine that this can vary a lot, but we did our best to interview a lot of miners and also to review literature to establish some average equivalence between that, because a part of the impacts, so ecosystem services, etc., they depend more on the area, while the mercury impact or health impacts depend on the amount of mercury, which is related to gold, average gold production. So we tried to develop this simple model to trace the mercury or establish a relationship between the models, the average mercury use and mercury consumption and health outcomes. So in one hand, we have the proportion of mercury that goes to rivers and will be at some point absorbed by fishes that in the Amazon can migrate for more than 2,000 kilometers. Some species can migrate. So, and on the other hand, we have the average contamination from a person, and we estimate what is the amount of gold that will maintain this hypothetical person contaminated at this level for his or her whole lifespan. So we have the key question here is, given a certain amount of mercury and methylmercury, how many people can be affected, considering all these average parameters of people weights and fish consumption, etc. So as I mentioned, we tried to link the amount of mercury that would be consumed by fish to the health outcomes, these three health outcomes that we consider, and the change in the relative risk of developing these health outcomes. So our health indicator here is the disability adjusted life years. So we use the DALI indicator to assess the average changes on health quality. And we then use, like, to translate these into monetary terms, we use the value of statistical life. So we can combine these two to get to an average of economic value loss. Our case study, I will present very quickly here, is in the northern part of the Brazilian Amazon, in the Yanomami indigenous land, which has been, like, heavily invaded by illegal gold miners. Here we considered, it's just an example of the variables we used, and the range of variables. So, for example, the amount of mercury used per kilogram of gold can vary. The proportion of mercury released into water also varies following the literature, methylation rate, etc. And here we have all other variables from the specific site in the Yanomami indigenous land, such as the population's weight, the daily consumption of fish, varying from rural and urban population, urban density, etc. And here we have the final results, which, considering only 1 year, so in 2020, 5 square kilometers were degraded by illegal small-scale gold mining in the Yanomami indigenous land. We estimated, given the average productivity, that more than 800 kilograms of gold were produced in 2020, using more than 2 tons of mercury on average. So from these 2 tons, a part of these was released into rivers, affecting, we estimated, around 44,000 people. Again, considering these cumulative impacts that will occur at some point, not only in 2020, but in 50 or 100 years after it's released into the waters. So we estimate that, like, 300 people would develop hypertension, 85 people would have myocardial infection and infarction, and 4 babies would be born with mild mental retardation. And here it's a very serious picture. We estimate that around $69 million occurred in terms of environmental and human health loss, only in terms of, or will occur in terms of health losses, only considering the mercury that was spilled in 2020. And these would be the size of the losses that not only the Yanomami indigenous land are suffering, but also people that live in cities nearby that will eat fishes, eat contaminated fishes from the nearby rivers. So as a result, we have the public prosecutors adopting these as their official methodology, and we already have very good and interesting cases of also the federal police using to sustain courts in the Brazilian Supreme Court using this methodology. And we have these defined amounts also increasing a lot, because before they didn't consider any value for mercury impacts. And this is, again, a very first and rough estimate, and which is helping a lot the public institutions to try to prevent illegal activities. And as a next step, we are adapting the calculator to Peru and Colombia. Right now, we are beginning a project funded by the World Bank, and we expected to adapt these parameters considering the country's context. Thank you very much. I'm open to questions. Thank you.
Thank you, Pedro. Very interesting tool. And as you see, I think you can see two questions or three questions in the chat. Pedro, do you see the?
Yeah, I have a problem coming back to the room here. I think I'm still sharing my screen. Oh, here. Sorry for that.
So you have question. The first question is from Gorsata Stilo. Sorry. Oh, I lost that. I think her question was whether the tool is available on the web.
Oh, here I see the first question. Here, is the methodology behind the calculator available online? Yes, the paper that we published is available online. I can share the PDF later if you can share your email. I can share it with you. The online tool provides only the basic and most relevant hypothesis and references. So the whole list of references can be found on the paper that we published. Okay. The second question, is it possible to include a tool in this calculator to change the proportion of gold and mercury? Some recent reports have shown 1:8 in Brazilian Amazon, thus the 1:2.6 could become conservative. Yes, you're right. So we tried to be very conservative in a series, in most of our parameters, given that we needed to use some hypotheses about the mercury contamination, etc. We try to be very conservative. So even considering the proportion of mercury to gold production. And yes, in the online calculator, it's not possible to change because we wanted to develop a simpler tool that is not too complex to people to understand. But we have the same tool in an Excel spreadsheet that we handled to the public prosecutors, where they can change all these other parameters, also not only the proportion, productivity, proportion of mercury and gold, and also the other daily parameters, for example, value of statistical life, etc. So yes, and we are just avoiding a little bit to make the online too complicated. We wanted to be more like pedagogical and have an easy access to the overall people. Okay. So thanks for the questions.
Pedro, I think I missed the first question, the one before the one you answered from Maria Elena.
Okay, sorry,
Did you
sorry
see
for that.
it?
Yes, sorry. While these efforts are very necessary, I'm very concerned about the possible use of this index and calculator. There are magical numbers that can be used to talk that there are no danger in some regions of the Amazon, even when contaminated fish is being commercialized for human consumption, in thousands of miles away from the gold mining. Even international commercialization of these fish is disconsidered. Yes, so first, I understand that some people can say that this is like seems magical numbers, but again, it's our first try to get some numbers at least to the public prosecutors. Otherwise, we wouldn't have any number and any penalty at all related to mercury. So again, we try to be very conservative in the estimations. And yes, you're right, because the fish can be commercialized in hundreds or thousands of miles away. But in this very rough model, we consider that a radius of, again, a conservative radius of 100 kilometers, that so the population can be affected in this shorter radius of distance. But again, you're right that the contamination can go much further than that.
If you can take up another question, there's another question at the last line.
Okay.
Do you consider expanding that will be on Brazil?
Yes, so we are expanding and adapting the tool to Peru and Colombia. We are beginning the project. We expect to finish the adaptation by the end of the year. So we will also train and do some capacity building with the institutions in these two countries. Again, the prosecutors in these countries, the Ministry of Environment, and we also plan to expand these to other Latin America countries such as Ecuador, Bolivia, Suriname, etc. Oh, okay, so that's the other is a comment by Alfonso. Oh yeah, I will leave my email address here. So feel free to contact me. I can share the study, and if I can present the methodology in more depth if you want later. But again, I really recommend the paper also that presents all the methodology in more depth.
So we have 3 minutes. So would it be a good time to close, or do you perhaps each of you may wish to say a few closing remarks? Alfonso, John, you can jump in if you wish.
Thank you, No, thank you so much, Pedro. Very interesting calculator. We can integrate both index and the calculator to get more integrate data in some point. And welcome to Colombia. You are try to work here. So let me know. We keep in touch. What happened in the future?
Thank you, Alfonso. I'm sure that combining, as you said, combining the Mercury index with the calculator could be a very interesting idea, as the index is much more refined that from a site-specific mine. Perhaps we can find a way to combine these two tools would be very interesting. So thank you again for the invitation and the opportunity to talk.
Okay. That's everything for our side, Isako. Thank you so much.
Thank you, thank you all. I think this is a very interesting chemistry to bring together the two methods. Of course, these are for different purposes, but there may be a cross fertilization and enrichment. So thank you very much. This is a very interesting session, and we still have 3 side events today before the COP4.1. So we look forward to seeing some of the audience in these events. So thank you very much. Have a good day, good night, good evening. Thank you.
Okay. Bye.
Thank you.